We're going to hear from Anadarko about some of their real-time drilling story. I think y'all guys presented at the Rice Data Science Conference.
Yeah, that's the first generation. We had a lot of improvement.
Okay.
2 years.
Okay, cool. Yeah, so Ding's going to talk to, he's a data science manager at Anadarko in the AAET team. And he's been, working there for quite some time. I did see it at Rice. It was a good presentation.
Yeah.
And so he got his PhD at Wayne State University. He's been doing machine learning and operational research for quite some time there. He's been helping build out the real-time drilling analytics effort. And so, take it away.
Okay. Yeah, it's working. Good morning, everyone. Thank you for joining our presentation. Today we are very honored to come here. I bring my whole team here to present what we had in the past 2 years. Yes, like John said, we present this one in Rice conference in 2017, and today we're going to present the progress in the last 2 years we had. So this is the outline of our presentation. First, I will recall what we had in the first generation and talking about the challenges we had in the past 2 years. And then I will go to the second generation of our real-time ecosystem. Because it's an expansion of the original system, and then we have a lot of other stuff add to it and make it running as smooth as possible. And in the ecosystem, we have 4 portions. The first portion is the analytics model. Today, we are going to focus on the ML model or the DL model. My colleague Yuxing will focus on the ML DL models. CPU is a very fantastic online and offline model. And I also present another DL model to identify the rotary steerable system downlink sequence. And after that, we will present our digital transformation solution, which enable the real-time top engine model, not just the top engine, but all the fixed-based model. And inside this, we will have 2 digital apps. One is the PWP Digitizer. I will give some insight to this. And the second one is the DPAT. My colleague Kay will give the detail on that one. And after that, I will talk about the cloud-based ML pipeline, which is important portion for our ecosystem. And if I still get time, I will talk about the streaming system, but that's not that important as we have, because I already presented this before. And finally, we will have my colleague Kay give you a demo on our UI, beautiful UI we built, and junior engineer love it. And finally, go to Q&A. Okay, this is our first generation real-time analytics system I presented in the Rice conference 2 years ago. From the picture, you can see that we have 3 layers. The data layer, which had the XML data pulling from the real-time XML data pulling from the vendor. And also we have the green portion, that's the MS SQL, that's the statistical well data, and also the EDMP Oracle database, that's the open world. Some of the contextual data we still need to pull, and we pull all the data in the data layer. And then go to the analytics layer, that's the playground for me and Yuxing as a data science. We build a lot of model, not just the ML model. We have statistics model, we have stream analytics model, we have ML DL model, and we have fixed-based model. But this is an old picture I take from the paper. But we will present that later. And after that, we'll go to the UI layer, which had in-memory database to catch the data, and finally feed to the UI, and also go to the terminal storage. So this is the 4th generation. But when we put the 4th generation system into production in 2017, we faced a lot of challenges. The first challenge and the biggest challenge is we put a lot of fixed-based model, like Yuxing build an ECD model, and I build a target model. We put in the system, it's not working. Why is it not working? Because the data is not there. As a real-time system, the data needs to come in the right time in the right format. If it's not, then nothing happens. So the malfunction of the fixed-based model due to the lack of the digital well data, that's the biggest issue. And we present a digital transformation solution to solve this problem. And the second one is we use the rule-based model before to identify the drilling state. And the accuracy is not very good. And we present the ML-DL solution, and Yuxing will give the detail on this one. She used the deep learning to get the accuracy up to 99.99, like the 24K goal. So that's the solution. And then once we had the ML model running 24/7 in the production system, we need to have a way to monitor or the performance of the model. Like, let's say, if the model performs good or not, we need to have some confidence. So that's why we need to have the ML pipeline to do the anomaly detection in the ML model in the production one. And also, if it's not performing good, we need to have mechanism to retrain the model. And also, this is streamline our RTD ML flow. So I will give a detail on that one. The last one is the data cap and the time gap in the streaming system. If I still get time, I will cover that one. This is our challenge. And the next one, we go to our ecosystem. You can see here from this picture, the bottom portion is still the open system. You have data coming from the vendor and the victim data, and go to the red portion actually is the streaming system. And the blue portion actually is the analytics model we build. We add a lot of ML or DL model into it. But the yellow portion is the digital transformation solution we propose. And the green portion is the ML pipeline we propose. And you can see that this is fully automated. In Anadarko, we don't want to have a remote support center. We don't. We just have this system running 24/7. And without anybody take a look on it except the junior engineer in the last box, that's the UI. In the Anadarko, any junior engineer can access to this UI if they connect to the internet, Anadarko network. So we are not a famous fans of the remote control support center. So this is our architecture. And next, I would like Yuxing, my colleague, to talk about the deep learning stuff.
So good morning, everybody. My name is Yuxing. I'm a data scientist at Anadarko. So today I'll talk about how we apply machine learning to real-time drilling data. So there are a lot of machine learning definitions on the internet. So these two, I picked these two because personally I like these two definitions. So the first definition is from 1959. So this definition tells which kind of problem machine learning can solve. So when typically for a typical computer programmer, you use a lot of the if-then statement. So, but for machine learning, it can identify patterns. Not only you can apply if-then statement, you can leverage the pattern recognition technology and then to recognize those patterns. And machine learning, so you learn from the data. So what data tells you is what you learned. And for the second definition, this is a recent definition came up by a professor in Carnegie Mellon University. So what he says is, so we have a task. So in this case, in the drilling, we want to identify the rig state. So rig state identification is your task. So the machine learning algorithm learns from the experience. The experience it does not only can include the data, but also it's a labeled data. So the labeling comes from the drilling engineer's experience. It comes from domain expert. So he labels data, gives the data some meanings, and then we can train the data to come up with a model. So the final step is the performance of the model. So you can define accuracy for any of the machine learning models, and then you can evaluate how good this model is. So this is a typical machine learning workflow in the machine learning world. So basically you take the historical data and then you clean up the data and then train the model. So then we need to deploy the model in the system. So if the new data come in, then the machine learning, we apply the algorithm to the new data and then do a prediction. However, so in the machine learning, so the truth is, the biggest assumption in the machine learning world is you assume your data distribution never changes. So for a deployed machine learning model, your data has to be assumed having the same distribution as your trained data. So we need to build this mechanism to monitor if there is a data like distribution shift. Then we need to build a machine learning, why Ding talks about, so then we need to build a machine learning pipeline to monitor this process. So traditionally, the rig state, there's no, so even if we deploy the model in the real-time system, so there's no ground truth come of the real-time system. Thank you. So right now we rely on UI to detect any inaccuracy of the model. So that's why we want to build a machine learning pipeline to monitor the whole process to automatically detect the accuracy of the model. And then we can retrain the model. So we can set up alert in the system to retrain the model. So here are some pictures I downloaded from the internet. So this is a very common neural network method used in the computer vision and domain. So it's called a convolutional neural network. So we apply this method to our real-time drilling data. So this model can tell, so either if you substitute an image into the model, it can tell you either a cat or either a dog. So in our application, so we actually segmented the time series data into a series of segments. For each segment, we treat it as an image. So for example, if so when we build the model, so for each image, we classify the we classify if it's a rotated drilling or slide drilling. So this is another techniques we applied to our real-time drilling data. So this method is still based on convolutional neural network, but it's called a semantic segmentation. So what this algorithm can do is, so it can identify each pixel in the picture. So for example, here, the red color represents the buildings, and then the purple color represents the cars, and then pink color represents the road. So in real-time application, we apply this the same technology, and then to identify what's each data point represent, which drilling state each data point represent. This is the first example I will tell you. Is we use the convolutional neural network to identify the rig state in real time. So as you know, some of the people in the audience may know, so in the unconventional world, we use, so current practice, we use the rocking during the slide drilling mode. So when you do rocking, your RPM and your you kind of oscillate your top drive, and then you generate, this is the RPM data, so as a function of the time. So this is has a lot of data in this image. So the blue color represents the rotate drilling, and then the green color represents the slide drilling. So as you can see, if we set up threshold to classify these two drilling state, So the red line, so that's a threshold we can put in. So it's hard to find your threshold. So in any place where you can put the red line, you cannot distinguish fully either the rotate drilling or slide drilling. So we apply a rule-based model. So it gives us 70% of accuracy for Delaware Basin. So 70%, if we miss, well, I can give you a sense like how much data we misclassified. So even for 90% of accuracy, so 90% of accuracy, so you will miss 1 day of drilling probably. So you will misclassify the rigs data for 1 day of drilling. So even for 99% of accuracy, so 99% of accuracy, so we will miss several hours of drilling state. So this is how we apply the convolutional neural network to time series data. So we use a moving window to cut the time series data into a series of images. And then for each image, we classify it as a rig state. So we actually went a journey when we develop and deploy this machine learning model. So currently we are, as we speak, we are in the stage of deploying our 6th version of the machine learning model. So we tried random forest tree at the beginning, and then we found out it doesn't perform well as we compare to convolutional neural network. So we also built a model for each basin initially. And then later on we realized that as long as we put the data from the 2 basins together, we can have a general model. And also at the beginning, we include the whole section in the training. The whole section, I mean, the vertical section or curve section or your lateral section. So, but then we found out actually when we deploy the model, when we need to identify the whole section, then we need the well pass data from the survey. So in some time, for some reason, if the survey data doesn't come in timely, then we won't have, we cannot run the model. So then later on, we remove this dependency, and then actually we found out we don't need that whole section to help us. So currently, we actually gather the data from 3 US basins. So we train the data from 40 wells, and then the accuracy is pretty good. So we are deploying that model right now. So this is the user cases for the ML model. So we deploy the model, we run the model in real time, 24-hour day, 7 days a week. And then we kind of calculate the KPI based on that ML model, and also we do a directional analysis. So Kate will show you, will give you a demo later. So there are some concepts I would like to emphasize. So we call this online machine learning model, offline machine learning model. So in the online machine learning model mode, we mean we do a real-time inference. So we train the model, we deploy the model in the real-time system. So every second, we have the streamed data coming into our system, and then we run the model. So that actually gives some limitation to the real-time model. So the model, we can only use the data up to the current moment. So we cannot use the data after the current moment. And secondly, the model execution time has to be less than 1 second typically. So the onshore data comes in every second as every second frequency. So if the window of the, so I talked about we use the window to cut time series data. So we cannot use a very large window, then it requires a larger buffer for our real-time system. But for offline model, so we can gather the data after the data is stored in any database, and then we can build a model. So we don't need to worry about too much about the execution time, and then this model can be more accurate. So this is another application we apply the machine learning model. So this we use this semantic segmentation method to get the risk data. So we developed the offline models based on this technology in the medical field. So now back to you. Thank you.
Yeah, thank you, Yuxing, for the detail on all the ML model. So I'm going to present another ML model I developed with Sam and Dong. So this model actually we quantify the lottery scalable system downlink sequence. Why we needed to do that real time? Because we want to drive more the efficiency out of the during operation. And then we treat this RS downlink recognition as an image segmentation problem. So then we use the UNet. That one was the Yuxing just present. Look like a big U. That's the UNet. And we train the model based on one single measurement. That's the standpipe pressure. And we use a second opinion mechanism. Why I say that is because we want to increase the accuracy. What is the second opinion? It looks like you go to see a doctor. If a doctor say, oh, you're sick, you don't trust that doctor, and you go to another doctor. If another doctor say the same thing, then you will trust, oh yeah, I'm sick. But if another doctor say, no, you're good, then you say, I'm okay. So that's why we call it second opinion mechanism. And here, what we do is we train a model A based on the standpipe pressure, and we train another model B based on the delta standpipe pressure. The delta is the rate of change of the standpipe pressure. So only two models tell me that, oh, that's a downlink, then it's the downlink. If it's not, then it's not downlink. So this is we call the second opinion mechanism. We use this for the online-offline model, and we use it in here. And the accuracy of the model is very high, it's almost 100%. And we use 31 wells the data, with the 21 is the motor well data, and 10 is the lottery scalable well data. Next, I will show you how it looks like. So you can see that the upper one is the standpipe pressure signal. You see, the bottom one actually is the delta standpipe pressure. And this is one image. This is the time series data. We cut this as one image. We dump into the model. The model tells us that, oh, this is 3 downlink. It's obviously because when you use your eye to see it. But when you do the time series, it's not that easy. So this one give us, and the next one we give another picture into the model. The model tell me that, oh no, they're not downlink there. So they're not downlink there, obviously. And the third one we give another picture into the model. Model give us another one. So at the same time we do for the model B. So let's give this image into it, the purple one, and we get 3 downlink. And then we have the second one, not downlink. The third one is 1 downlink. So actually, you can see that 2 models identify how many 4 downlink. So that's the way we do right now. And the next one, I will give you the solution we use to solve the problem for the contextual well data. First, I will give a simple example. So this is the equation. If you want to know the speed, you need to know the distance and the time. Any of this one missing, you cannot, the equation will not work. So the same for the talk engine model. Talk engine model is a fixed-based model. It's with the bunch of equation on site. They need a bottom hole assembly, casing information, whole information, that kind of stuff. Any of this missing, the model will not work. But the problem for the oil and gas, especially for the operator, the well information is in different location, in different format. I say different location is like spreads everywhere, in your computer, in my computer, in this L drive, that SharePoint site, another SharePoint site. Different format, that means it's in Excel, in Word document, in text file, in whatever, or like images sometimes. So this is the headache for the operator. I'm not sure in other industry, but I work for 2 companies. One is BP, one is Anadarko. We both had the same problem. So when we try to make the model working, but the model is not working because they don't have the data to feed, what should we do? We propose that solution here. So you can see here the red portion actually is the easiest data infrastructure. So let's say this is the open well. You can see the open well, and also we use the open well and all the other database. The problem from the red portion is It had missing data, and the data is not updated that frequent. Like the OpenWell right now is update daily, at 6 a.m. in the morning every day. But we are a real-time system. We don't want to wait for another 24 hours to get the feed or the update, something like that. Anyway, that's the reality. So what we do, we build another apps to fill the gap. The new app will fill the data during the well-planned phase. The well-planned phase, and we have this app and digitize the information and say to the database so the real-time system can feed. So you can see the green portion. The two apps get the data and put into the MS SQL. And then the red one also had the Oracle database. And then finally we had the ETL in the middle of that. I should have the pointer, but the ETL, and put the data and feed into the right side. Actually, the gray one actually is the Tongue model, and we feed to the model. And the yellow one in the bottom actually is the real-time system. When the real-time data coming, like the survey data, the real-time survey data coming, they will send the data to the API, and then the translator will trigger the calculation and go and feedback the data, the result to the red portion, the yellow one, and then all the way down to the downstream. That's our solution. And this is not just for the talk-engine model. Talk-engine model is just for the POC, the proof of concept. This laid the foundation for any real-time fixed-based modeling, like the ECD was Yuxing built 2 years ago. We haven't put into production. It's because this problem. And other like the real-time BHA modeling. This is the solution we present. And the next one, I will go to the apps. We had two apps. When we built the two apps, we had a principle. Because we want the solution to be success or work. So we had a principle. Kay and me and Jian Yong, three of us, we spent more than 18 months building these two apps. When we built the app, we had a principle that we don't want to add new workflow for the end user. Our end user is the junior engineer or the operation team. What they have right now, we don't want to change. We don't want to choose the wrong beta to 5 years. We just want our system to run. We are not the people who introduce or them the fancy technology. We don't care about fancy technology. So what we do is we don't introduce any new workflow. Instead, we design to fit into the current existing workflow and streamline if they are not very optimal. We will streamline and optimize the process, but we don't change what they do. They do whatever they do daily. That's the principle. And this principle helps us to a great success in these two apps. And then the people love it because it helps them in the daily life. And at the same time, this app will digitize and collect the contextual data, automatically put in the database so the real-time system can consume. The two apps, because the one is the PWP Digitizer. It's an automated data pipeline to digitize and collect the PWP. I will explain to you what is the PWP later. And also the during program automation tool, we call it the DPAT. And Kay later will give a detailed insight on this one, because she and Jian Yong spend a lot of time on this one. And what's the PWP? PWP is like this. This is our beautiful UI. Kay will give a demo later. But you can see the line, the blue line, the 3D plot, the blue line. Actually, that's the PWP. Without that one, you're not able to do the 3D plot. And the red one actually is the actual survey. The actual, when we drill in the middle, so you can see this drill in the middle, the red one. So the PWP is very important. And to be honest, this 3D plot is the junior engineer's favorite function in the RTD system. And also the PWP is very important for a lot of fixed-based model input, like the talk-engine model. You need to have the PWP or survey to do the calculation. And the PWP Digitizer is a data pipeline fit into the existing PWP approval workflow and digitize the PWP automatically. Now I will give you the workflow. Okay, the current working flow is very simple. The directional company use the email, send the PWP to the junior engineer via the email. And the junior engineer will reply the email if they think he approved the PWP. That's our current workflow. You may think that's the 80s workflow, old-fashioned, but I don't mind, because that's how we do right now in US onshore. So what we do is, like, for the green portion, we build an application in the back end, monitor the email. When the email comes from the direction company, with the attachment of the plan well pair, the app, Daniel and me and Kay build, will download the attachment and extract the plan well pair and do a data quality check. If the data is good, then we'll dump to the MSC call. If it's not good, then we will send the email to back to the direction company, say, dude, your data is not good, can you do resubmit? That's how simple it is. And even the juniors then doesn't know what happened in the back scene, because we don't have any people manually do anything. It's just big into. You can see the yellow portion is the front end, but the front end is just like some email notification if the plan well pair is not good and cannot put into the database. That's how easy it is. And the next, I will let my colleague Kay to talk about the DPAT. That's another app we built more than 18 months. Yep, thank you.
Okay, so Ding covered how we're able to get that directional plan ahead of time. And this solution, the Drilling Program Automation Tool, DPAT for short, is how we get the rest of the data that our models need. So it's really a win-win development, because we're able to digitize the casing, hull section, and BHA data that our models need, while also reducing the time it takes for an engineer to create a drilling plan, and also improving the accuracy of the data that they include in that plan. So it's a desktop app, and it compiles data from multiple databases and then outputs the content needed by the engineer and the rig, and also delivers our needed data back to our MS SQL database. So the first step for the engineer is offset research. And the DPAT tool enables on-demand analysis of offset wells. So the engineers are able to choose the radius they want to look at, then dial into exactly which wells within that radius that they're interested in, based on formation zone or lateral length or a couple other options. And they can generate a 3D plot, as you see on the upper left picture, and that will show their planned well path in the context of the other wells that already exist downhole. And this can help them understand if the directional planner actually created the trajectory that they had in mind, and make sure that all the necessary wells are included on their anti-collision report. Next, to the right, you see an MPT and phase duration breakdown, and this helps the engineer see where trouble was encountered in the past or where performance was excellent. And then within DPAT, they can access the daily drilling reports to dial into the details of the exact events that they're interested in, where they can see, do I want to copy that, or do I want to avoid what they did? And on the bottom, you see mud weight versus depth and days versus depth, which gives a frame of reference for past performance for both the engineer and the rig. So in the time that they save by not worrying about complex queries from multiple databases and manipulating data and simply waiting for Spotfire to open, they can focus on the insights that they can gain from these visuals and focus on planning a well that's going to be executed in the most efficient manner. The next step for them is the wellbore diagram generation. You can see an image of what DPAT generates on the right, and this is an Excel file. And this is, again, part of that win-win strategy. This is the format that they're used to. This is the format that the field likes to see everything in. So we've given them that format, even though it's not the most beautiful. What we've done to help them is autofilling a lot of the information that they manually would type. They have the PDF of the GeoProg open on one screen, the Excel file on the other, and they're retyping all these tops. So instead, we have a direct link to the geologic database, and that also ensures that they always have the most up-to-date prog within their program. We're also able to collect data out of this wellbore diagram, such as the hole sizes, casing sizes, and shoe depths, which is necessary for our model. And we'll send all that back to our SQL database. And finally, the BHA details, which actually enables the real-time automated physics-based models to run at all times. Again, for the win-win strategy, we've delivered this table you see at the bottom, which shows all the BHA details and mud properties in the format that the engineers in the field like to see it in. So we deliver that final product to them, and in return we get to collect all that data and send it to our database for consumption. Another nice feature we've added for the engineers is the ability to pull BHAs that were previously submitted, so they don't have to go dig out their old progs from the last well. They can just double click in that list on the right, and their BHAs from the last well will just auto-populate in the table. They can make any small changes and resubmit to the database. In the future, we'll integrate the ECD model and torque and drag model within DPAT so that engineers can assess their trajectory, BHA, and mud property plans ahead of time, make adjustments as needed, all during the planning phase before the rig ever arrives on location.
Thank you, Kay, for the great work in the DPAT. The next one, I will introduce our ML pipeline. I will start with the motivation. Yeah, you can see the previous plot. This is the green portion. The motivation is like when we had a model running 24/7, we need to have a way to automatically detect the anomaly of the model, like the model is not doing good. Because you know that ML model is trained based on some of the historic data. If the incoming data going to the model had, like Yuxing say, the distribution or something changed, the model will not working properly. So we build a ML pipeline to automate anomaly detect the production ML model. But you use the second opinion mechanism. We call it the offline online. So let's say we build a real-time model, do the real-time inference every single second. But we also build an offline model. At the night, like 2 a.m. each day, we'll pull the past 24-hour data and dump into the offline model. And then we will compare the online model, offline model result. If they are not consistent, that means the two doctors tell the different story. Then we know that some doctors maybe is not good. That the real-time one is always not good because we are assuming that offline model is more accuracy than the online model because the offline model have more data than the online model and doesn't have the constraint. And then by this way, we can retrain mechanism for the production ML model. And also, we also streamline our working flow. You will see later, is a big improvement. And you see, this is our original ML workflow. We had the Google Cloud in the up, we had the Anadarko in the down. You can see that in this side, here is the rig data come from the rig, go into the real-time system, go all the way to the MongoDB. That's the database. We say the result feed to the UI. The UI will be here, but I don't put it there. Right now, what we do is we using or the junior engineer like Kay need to go to the Google Cloud and pull the data out, put into a local computer, use the Spoke file or like the Excel or the Python to manipulate the data and prepare the training test set, and finally rebuild the model, use our NVIDIA DCX box. And pulling the data out of the cloud costs money and time. Like last time we pulled 20 gigabit data, take about 5 hours. Don't mention we need to pay Google when we pull out. And when we build the model, we need to move the data back to the Google Cloud. You see that? The same data set, we need to, the training and test data, we need to move back. And also the model, the way of the model, we need to move back. And here, we need to rebuild the model in the Cloud ML engine. And then deploy the model, and the real-time system can do the inference. So it doesn't make any sense. It's a big data set migration between the cloud and Anadarko. And also, we need to rebuild the model in the cloud. That's ridiculous. But that's how we have right now. And it's not a streamlined workflow. So what we do, we remove the bottom block. You can see everything is in the cloud right now. It's the Google Cloud right now. And the same, the data coming to the real-time system go to the MongoDB. Not problem. But we don't move out the data anymore. We just play the data inside the GCP, use the data studio or whatever, and prepare the training data and test data. and we retrain the model, use the Google Cloud ML engine, and then we deploy the model in the Google Kubernetes engine, and then the real-time system can inference. And this is the yellow one is the regular ML workflow. And then we have the blue portion, actually we call it the retrain ML workflow. That's the second opinion I told you guys before. So every day, like 2 a.m. in the morning, we will go to pull the data for the past 24 hours. We dump into the offline model. We get the result of the prediction result of the offline model, and then we compare the result of the real-time model and the offline model. If they are not consistent, like let's say 5% or 2% of the data of the past one way is not consistent, then we will retrigger the training, and then train the model, use the update data, and deploy the update model into the GKE, the Google Kubernetes engine. At the same time, we need to update the real-time model result because this UI use this one. So that's, in this way, then we have streamlined real-time RTD ML workflow, and we have auto anomaly detection of the model because we use the second opinion. Oh, that's an option, that's a typo. Okay. and then we have the retrain and chain mechanism. And then the challenge is like, do you guys watch the challenge? The challenge is the oil and gas guy love the Spotify. Everybody loves Spotify. I love Spotify because I use Spotify to visualize the data a lot. But here we need to eliminate the Spotify. But that's a challenge we need to address, and should be good. I will skip this one. Okay. I think they need to click the video.
Okay, so here's a demo of our web-based app. All our analytics are processed in real time, so the end users always have the most up-to-date view of what's going on. First, we'll see a dashboard, which allows anyone in the business to get an understanding of what's currently happening on a given well, and also a summary of what's occurred over the past 24 hours. Next, we'll look at how we can select other wells and rigs and other groups to compare the current well to those. So this is the neighboring well, and then the rig and all the historic wells associated with that rig. So we can compare this well with past performance of the same people. Next, on our KPI page, we make use of that operational state that we've assigned to each second of data. And like Yuxing talked about, we were able to break out the rotate versus slide drilling. And so you see rotation in blue and slide in red, and we can compare the rates of penetration for each operation, as well as overall footage and time, and we can also look at the different off-bottom time operations that we've classified. You can see the filter capability up at the top of the page, and that can allow users to select specific BHAs or just look at certain times of day or parts of the well, and then compare those same KPIs for each of the selections. You can also see the connection time plots at the bottom of the page, and our models allow us to provide very granular detail about the operations associated with making a connection. And simply by virtue of providing this data to the operations team, we've seen huge performance gains in connection time. We can also compare these same KPIs across those rigs and wells that we selected earlier. So here we can see that the current well and the offset well are far outperforming the historic rig performance in tripping time and also in slide and rotate ROP. Our management team finds this really helpful to compare quarter-over-quarter performance or different rigs or regions against each other. The 3D plot allows on-demand trajectory analysis, so you can see your plan versus actual, and also you see the context of the other wells that are either already in existence downhole or planned to be drilled in the future. So of course, there's software available for engineers to create this visual on their own, but those are usually very time consuming, which translates to they don't, especially not multiple times per day, as this is usually referenced. As Ding said, this is one of our more popular pages, and we see a lot of geologists loving this page as well. We can also take a zoomed out view of the complete development plan as well. The tool face plot is a critical tool for diagnosing slide drilling inefficiencies, like poor tool face control or overcompensating drillers, or we call it painting the line syndrome. We've also seen it used for rotational trend analysis as well. So this tool can help engineers make real-time decisions like whether to trip or not, and can also be used as look-back tools to identify opportunities that may have been missed in real time, or to compare different personnel or BHA performance. So there you have it, our RTD system as of today, but we're constantly adding new enhancements and new modules and constantly improving the application.
Thank you, Kate. So here I want to take this opportunity to thank our team, the great development team. So they really did a great job, and you can see the name here. So I will introduce my team here. So actually, where's my pointer? Okay, here. So Shreyas MT is actually the stream-based developer. It's a Java developer which worked with me to take care of the back-end real-time system. So all the real-time system, the back end of the streaming system is built based on the typical stream-based. Original in 2017, I worked with the typical to build the system. But right now, I gradually hand over the system level development and maintenance to these two gentlemen, and I just handle the in charge of the model side. And Daniel and Seth, these two gentlemen, build the beautiful UI that Kate just saw. They really do a great job. And Daniel worked with me and Kay to build the two digital app with about 18 months. And Shen, Wei Lu, Dong, Ryan, and Daniel, they train the ML model or deploy the ML model, and also they build the ML highlight and the RTD Ecosystem solution. So I really appreciate their great work. And then here is our management team, the leadership team. We also appreciate the management support from the leadership team. And of course, we also appreciate all the support, helps, feedback we get from our colleague in Anadarko regarding the RTD project. And let's see what the next one is. Okay, the next one is our paper. We have a ton of paper. So if this presentation is based on the paper or our paper. If you want to know more detail, we will have one paper coming out at ATCE this September, and Yuxing will present the ML model in the OTEC this July. And next year in the July conference in 2020 in Galveston, we will have 3 papers coming out, hopefully. Yeah, so this is our paper. And thank you. Let's see how many time we have. We have almost 11 minutes. Yeah, just ask question if you like. Oh, we already have some questions. Yuxing, can you answer this one?
This one works or not?
This is working? Come here.
Well, actually, most time the semantic segmentation for this problem works very well. We apply this to the offline risk data identification problem, and also didn't apply this semantic segmentation to the downlink identification problem. So sometimes you will miss some of the data in between. For example, if you have a series of data points which represent the slide drilling, you may miss some of those points in between. But we have, well, I didn't say that, but we have a post-processing procedure you can apply. You can use your domain knowledge to, for example, you can say if the 90% of your data point represent slide drilling, use that particular interval, then it means that the whole interval is slide drilling. So it can be overcome.
Yeah, let me add something to this one. Yeah, I also reply. Thank you using on this one. I also use the image segmentation. My conclusion is like, for this one, we use a time series data. I don't use the traditional time series method to play with this. Instead, I just convert to an image and let the model take care of it. So my feeling is like, anything the human eye can identify from a picture, the machine will get it. Let's say if the picture had a dog, the machine will pick the dog out. The same here, when we had the downlink or we have another algorithm, like right now I work with K on the completion side, the real-time completion side. We use the image segmentation. If the human being can pick that one, machine will pick that one. So it's easy and it's the fast way we can put the model into production. So we don't go back to the traditional time series methodology to play with, and you may spend a lot of effort finally get the same result as the deep learning, the image segmentation. Yeah, that's my feeling. So the second one is not a question, right? But I still want to comment a little bit. Because really, that's the feeling me and Kay and Jianyong. In the past 18 months, we built the DPAT and the PWP Digitizer. Some people doesn't like it. They say maybe, oh, your technology is too old. But we don't care. We don't care about technology. We are not the guy who advocate the fancy or the flex technology, because that doesn't bring value to the operation team or engineering team. What we care is whether we made them happy and they made us happy. So we give them a tool, make their daily life easy, and they had to use the tool to make our system running. That's it. So yes, it's a win-win. How is the? We don't do any MPT prediction, right? We don't.
I can make some comments. For the non-PT prediction, so we tried some problem internally, but I think the biggest challenge is you need to identify the right problem quite often. So your from a data science point of view, if for a non-productive time prediction, you have unbalanced data, so makes the training very difficult. And also, like, what's the business value can bring when you predict the non-productive time? If it happens, always. So even you predict it's going to happen, it won't help. It won't help you. Okay, so we labeled 40 million rows of data, 30 million rows data from 40 wells. We picked from 3 US onshore basins, Delaware, DJ, and Powder River Basin. Well, our drilling engineer, Chris James, is quite a smart guy. He actually didn't label it row by row. So he actually wrote a spot fire program to help him correct the mislabeled data. So still, I think for the first round, it take him probably 10 hours to label, I think, 10 million rows data. And later on, he told me he found a better way to do it, so he can do it very fast.
How is the impact of from the beginning?
Okay, so how is this impacting the use of current commercial portfolio of drilling software? I would say it's not really impacting in a negative way. Although it does provide engineers some insight into when they should go into those packages and make the detailed models of their wells, when they could be seeing some signs that, okay, I probably should go in and really dial into my torque and drag model. That portion of RTD is not active right now, so they're still using the software package for stuff like that right now anyway. And then what types of engineers are using the software? I think that was the question. Our main users are the drilling engineers who actually run rigs, and then their management teams. And also the geologists have started using this as well. The toolface plot is another thing they use besides the 3D plot, and they can get a feel for how slides are reacting in certain zones. I think another question was about gamma, and yes, we have thought about including that. So right now they're using their interpretation of gamma in combination with the toolface plot to understand how the bit is reacting to different types of rock. including how the driller is reacting to that, and being able to make decisions with the drilling engineer. And that's been really helpful for just optimizing, is it really important to make this plan change right now, or can we just continue on with what we're doing and save some time?
I think you're using only 10 tens of the well?
No,
Okay.
sorry. Actually, for first round of training, we use data from, I think, over 20 wells from 2 basins. Actually, that are very representative because for each well, it has, for the longer well, it has over 1 million rows of data. So we use a moving window when we train the model. Actually, it's generated over 10 million of image. So we have a big data set. So we have to run the model in a single GPU to get the model trained. So there is no, I don't think there will be overfitting issues.
I think that for the tank well, maybe it's talking about the downlink version. Maybe that one, I think we use the tank well for the RSS well, but we also use the 21 well for the mud water well. So it's good. But right now the model, we have monitored the overfit problem, but we don't see any right now. And we are testing the model and ready for production. And the last question is the prototype. We are not building a prototype. The system is in production. It's not a prototype. Kate, you answer the second one?
So the drilling supervisors, not all of the on-site PICs have access to the system right now. We have about 5 guys who are using it and then can provide feedback to their drillers or directional drillers based on it, and they're really loving it. And the other guys that don't have access are receiving still shots from it, for instance, the connection plot, and they're really loving having that data there. Some guys used to have stopwatches and time the rig crew making a connection, and now they don't have to do that anymore. They just can get in the morning report, have a screenshot of all the connections over the past 24 hours, and then let the guys know, hey, the night crew beat you, so try harder today.
What the well? I think the well view.
Yeah, we use the landmark suite.
Yeah, I will answer the GCP one. So in the GCP, we use the BigQuery, Bigtable, we use the bucket, we use the Cloud ML engine, and what else we use? We use PubSub. PubSub not in the RTD, in RTC maybe. Yeah. So that's the technique we use, the tool or service we use in the GCP. What has to be how high? So the resistance is like 2017. We put the system in the production, but because now the model is not working, so the user will not use it. That makes sense. And 2018, we focused on solving the problem, and then I think they are good, right? That question.
Yeah, we've also provided the logic on a wiki, so engineers can actually go in and see how calculations are made, and then feel good about the data being provided and trust it. And as far as the field, like I mentioned, they love having these diagnostics available to them very easily.
Yeah, I think the time is almost up. Let me see one more question I'm to answer. Detect. Yeah. What title? For the vendor one, we don't have any vendor involved into our current RTD project. So that's all built in internally. So for another tool, just talk to me offline and then we can discuss. Thank you for everyone. Thank you for the chance to present here.